We can relate intermolecular forces to some of the properties between the states. Two of them that we can relate to is changes in state. Melting point, which is the temperature where a solid turns into a liquid. And boiling point, the point where a liquid turns into a vapor, are both influenced by intermolecular forces. In this case, the stronger the intermolecular forces, and when comparing two compounds, leads to higher boiling points and higher melting points. This makes sense because the stronger the intermolecular forces, the more tightly the molecules are held to each other, which then increases the energy needed to boil and melt. Now, when talking about liquids, there's several properties that are also influenced by intermolecular forces. So when we know that liquids go to gas, we call it evaporation when the liquid goes to gas, and then condensation occurs when a gas goes to a liquid. In this process, when evaporation and condensation are at equilibrium, we get something called a vapor pressure. And a vapor pressure is the pressure exerted by the gas molecule when they are in equilibrium with its, liquid. I kind of think about this as the escaping tendency of the gas. So things that have high vapor pressures means that a lot of gas escapes from its liquid. They evaporate very easily. So if you have a high vapor pressure, it means that your gases escape easily from the liquid phase. So that means, again, that you evaporate easily, like alcohols or gasoline. Things with lower vapor pressures, the molecules are held more tightly as a liquid, and so fewer gas molecules escape. Now, one thing that can change the vapor pressure or how much gas is escaping is the temperature. If you increase the temperature of your system, you will increase the amount of gas that's escaping, and so you increase the vapor pressure. I know it's kind of weird to think about a vapor pressure being a property of a liquid, but remember, what we're measuring is the gas escaping from that liquid. In fact, this is very relevant to our boiling points. The definition of boiling point is at the temperature where, look what happens, the vapor pressure is equal to the atmospheric pressure. So when the pressure of the atmosphere pushing down on your liquid, so let's say I have a container, and inside my container is a liquid. And that liquid has gas molecules that are escaping. You know, even if you just set water outside, eventually all the gas molecules escape and it evaporates completely. Well, it's the vapor pressure. That's what the gas molecules escaping. Now, let's say they're escaping. When something will boil is when the atmosphere, when it's pushing down with the same pressure as the gas pressure that is pushing up, then the liquid will boil. It's kind of interesting because it means that boiling, the temperature something boils, is related to the atmospheric pressure, which means this can change depending on your elevation. Because the higher the elevation, the lower the atmospheric pressure. Now, if I ask you today, what's the boiling point of water? You would probably tell me 100 degrees Celsius. And that is the normal boiling point of water, which occurs at 760 atmospheres, 760 millimeters of mercury. It occurs at 1 atmosphere. 1 atmosphere is atmospheric pressure at sea level. So here where we are at 1 atmosphere, we would expect our water to boil right around 100 degrees. If you go higher in elevation, like somewhere like Denver, your water actually boils at a lower temperature because the atmospheric pressure is lower. So back to those intermolecular forces and how they affect vapor pressure. Well, if you look here, stronger intermolecular forces. Intermolecular forces have an effect on vapor pressure. So the stronger they are, the lower the vapor pressure is. It makes sense because vapor pressure is gas escaping. And if you're held together tightly with a strong intermolecular force, then fewer gas molecules escape. So stronger intermolecular forces lead to lower vapor pressures. And lower vapor pressures lead to a higher boiling point. That's because if you have a lower vapor pressure, it requires more energy and more heat to raise the temperature so that the vapor pressure equals the atmospheric pressure. So strong intermolecular forces, the stronger they are, is related to lower vapor pressures and to higher boiling points. Two other, and for us less common, properties of a gas that we can relate to intermolecular forces are viscosity and surface tension. So viscosity is the resistance to flow. So things that have a high viscosity move very slowly because it's their resistance to flowing, like molasses. Surface tension is the resistance of a liquid to spread out. So things that form little bubbles very easily or little droplets very easily would have a high surface tension. And again, intermolecular forces, the strength of them are related to that. So the stronger the intermolecular forces, you would have a greater resistance to flow because the molecules are all held together and you have a higher viscosity. Stronger intermolecular forces would also have you resist the liquid resist the spreading out, and so stronger intermolecular forces would lead to higher surface tension. Now, some of these things, if you can kind of wrap your head around or make cartoons in your brain about what the definitions are, you might understand better about how the intermolecular forces affect it. I always just want to think about, though, what a stronger intermolecular force does is hold your molecules tightly together. And so when you're thinking about the different things and how it affects it, think how would it affect the molecules if it was held more tightly together, because that's what the stronger intermolecular forces do. You know, you could also write these in opposite, and I'll only do it for the last one just to make sure you understand. But if I said instead weaker intermolecular forces, it would have the opposite effect. So instead of higher viscosity, it would have lower viscosity. And instead of higher surface tension, it would have lower surface tension. So all of the examples that I've written, you could write it in opposites if you wanted to start with weaker intermolecular forces. I just chose to write them all in terms of stronger intermolecular forces.